All right, today we're going to look at the next method of proof. That's your next test score then. Indirect proof. Now, do you guys remember doing indirect proof when we did logic?
Yes.
Really? Man, we did all that stuff, man. You guys just...
You might come back, but...
And what would happen? Look, you guys are the good students. If the good students purge, just imagine the regular ones. Okay, so these are like 2 out of the 3. These are very classical proofs. I'm gonna do number 9 for you. In fact, I was gonna do them all, and then that's the homework. Just know how to do it, because 2 out of these 3 is gonna be on the test.
Can we do number 2, Mr. Park? Or the
Okay, so here, I'm gonna show you how indirect proof works with number 9, and then we'll just go through 10 and 11 really quickly. If a squared is even, then a must be even. Okay, so sometimes it's too difficult to do a deductive proof, so we do an indirect proof. I was hoping you guys would remember the logic, but no. So what we're going to do is we're going to suppose, the first step in an indirect proof is to suppose that this statement is false. Does that sound familiar?
Yes.
Okay, we're going to suppose that it's false, and then if it's false, what we're hoping to get is a contradiction. Does that sound familiar?
Mm-hmm.
And then, if we get a contradiction, that means this statement wasn't false, it was true.
Yes.
So, suppose that this statement is false.
A squared is odd.
If a squared is even, then a is odd. It is odd. It is
Oh
not.
yeah, it is. Okay,
It
so
is
suppose
not.
that a squared is odd, then yeah.
No, we're gonna no. I guess we forgot our logic. Okay, logic review. What is the negation of P implies Q?
What?
Negation,
not
not
P.
P.
P,
Implies not Q.
no. Okay,
P
how
or
do you
not.
convert a conditional to an or statement?
P or
P.
not.
Negate the first, leave the second one alone, right? So what is the negation of that then? What's the negation of not P or Q?
P and Q.
P and not Q.
Not Q. Like that.
Okay, so the negation of this statement would be this and not that. Oh my goodness.
A squared is even and a is odd.
Okay, so
Oh, but then that's
wait, time out. Did we do this on last night's homework?
No, we didn't.
No.
Good.
Oh no. We proved on last night's homework if A is even,
Oh,
then
the other
A
one.
squared is even. This is the
Opposite.
If and only
what's that called? The converse of that.
Converse.
Okay, so suppose A squared is even
and a is
and A is odd. See? So what you want to suppose that this is not true. Right? So the negation of that is this. So what you do is you work with this until you get a contradiction.
Oh, that's
And if you get a contradiction, then that means the original statement was true.
yeah, because 2 and plus 1
Okay,
is
so-
oh, yeah.
And look, remember your logic? If you have an and statement that's true, doesn't that mean both of them are true?
Mm-hmm.
Okay, so which one do you want to start with? Let's start with
A
this
is
one.
odd
So
and
if A is odd by definition, then what? A is equal to
2k plus
2k plus 1 for some integer k, correct?
and then square.
Square both sides. A squared is equal to 4k squared plus 4k plus 1, which is equal to 2 times something plus 1. And what is that something? 2k squared plus 2k. Now, if k is an integer, then can we say that's an integer?
Yeah.
Yeah, because of the closure property of addition and multiplication, right, for integers. So therefore, what can we conclude from
A
this?
squared's odd, but that's
A squared is odd, which contradicts this statement here. So this is a contradiction. See, that's what you want when you do an indirect proof, is you want a contradiction, which means your supposition that this was false is wrong. That means this one is true. That's called indirect proof. See how we did it indirectly?
That sounds good.
No, for real. Does anybody even remember a little
Yeah.
bit about indirect proof from logic?
I remember.
Yeah.
I remember.
Okay.
We just got a bunch of statements and did the same thing as this.
Okay, these next 2 proofs, okay, you know what? One of these will be on the next test. These are 2 classical proofs. Number 10, and they were both done by Euclid. The square root of 2 is irrational.
Suppose it's rational.
Okay, so how do you prove this statement indirectly? Well, the first thing you do is suppose
It's rational.
radical 2 is not irrational, which means it's rational. Now, what is the definition of a rational number?
It can be represented as a over b, where a and your integers and
An integer over an integer, right?
Yeah.
So that means the square root of 2 is equal to an integer over an integer where
A, b are
a
integers.
over b is in lowest terms. That means it's reduced.
And a, b.
Yeah, I guess we gotta say a and b are elements of the integers. Everybody understand that? This is the key part to the proof. A over b is in lowest terms, because that's where we're gonna get our contradiction. Okay, everybody understand so far? So now all you gotta do is work with this. How do I work with this? Yoshida, you already did it.
Oh yeah,
Before
so
class.
if you square it.
Square both sides. So 2 is equal to a squared over b
squared.
squared, which means a squared is equal to 2 times b squared. But,
What?
Conjugate.
no, we don't have to. This is last night's homework. If a squared is equal to 2 times an integer,
Oh, even.
a squared is even.
Oh, a is even.
A squared is even, but then by this thing that we just proved,
A
a is even,
Yes.
right?
Mhm.
If a squared is even, then a is even. That's why I gave you that one
Now
first,
I
so that we can use it in here.
B
But
is
if a is even, according to the definition, a gotta equal to
2K.
Oh,
okay,
and b must be
2k for some integer k.
Yes.
Okay, now what do you think I'm gonna do
Plug
then?
it back into the
I'm gonna
square.
substitute it back
And
into
it's
this
4.
equation. So
Oh.
if I substitute it back into here, you get 2k quantity squared is equal to 2b squared. 4k squared is equal to 2b squared. Therefore, b squared is equal to
2K squared.
2k squared. But then b squared is equal to 2 times an integer.
Even.
But then
So
b-
therefore, I'm gonna go up here,
Oh my.
b squared is even.
But then it's not in low
B is
terms.
even.
Wait, not yet.
Yeah.
But then according to this
Oh, then it's
theorem,
B.
then b gotta be even.
But then it's not in low.
Now do you see the contradiction?
Yeah.
How can A be even and B be even if it's in lowest terms? Because if you had an even number over an even number, you can reduce it down. So there's your contradiction. Contradiction.
Oh, okay, that's,
So therefore, that statement is true. Isn't that pretty neat?
yeah, that's.
Anyway, another name for indirect proof is called reductio ad absurdum. Who takes left in here?
Reduction by
Explanation.
something.
Reduction to absurdity.
Something.
See, the absurdity is the contradiction. If A over B is in lowest terms, then how can both A be even and B be even? Cannot. That's the contradiction. Okay, last one, and we're going to look.
Oh, this one's super cool.
Yeah, this is probably the most famous proof in the whole world. Well, it's simple proof.
Infinitely many prime numbers.
Oh.
We should try to prove, or we should have someone try
There
to
are infinitely many
Do we need mod?
No, you just sum them
prime
and you add
numbers.
or you multiply them.
No, it kind of makes sense that there are infinitely many,
Oh,
but
because
we need a proof.
one added number is
Yeah.
still a prime.
Okay, so
Yeah.
so
Oh, I see,
suppose.
I see, I see.
Okay, so
I think we're
suppose we gotta suppose that this is false. So suppose there is
Oh,
a
yeah. that-
finite number of
Yeah,
prime
I
numbers,
did it.
finite
I did it.
number of primes.
And then
Okay,
like
everybody
list-
follow me?
maybe create a list, one
Okay.
P1 through Pn.
Okay, so suppose there's a finite number of primes. Then if there is a finite number of primes, wouldn't there be a biggest one then?
Yes.
So then there must be a largest prime.
Yeah, you just find out.
Let's call it P.
Larger.
Let's call it P. Okay, so everybody following so far? So we're going to suppose there's a finite number of them. And if there's a finite number of them that has to be a biggest one, we're going to call the biggest one P. Now, consider this number. Consider the number. Okay, so we start with 2. 2 is the smallest prime number, right? And we're going to multiply all the prime numbers up.
2p.
So here are all the prime numbers, and what's the biggest one?
p and
To p,
okay.
and then we're gonna add 1 to it. Now, consider this number. What can you say about this number? Well, we gotta go through the steps. Is this number divisible by 2?
No.
Yeah.
No.
No, look.
Because there's a 1.
Yeah, because if you divide it by 2, you're gonna get 1 left over, so it's not divisible. Is this number divisible by 3? No, because when you divide it by 3, you get 1 left over. See this plus 1, that's all. Is this number divisible by 5?
No.
No, because you get 1 left over if you divide it by 5. What about 7?
No.
11,
No.
13,
No.
17,
No.
all the way to p.
Yeah.
So if this number is not divisible by all the prime numbers, then what can we say about this number? It's prime. So this number has to be prime.
Contradiction.
Does anybody see a contradiction?
It's the largest.
We said that p is the largest prime, but we just found a prime number bigger than that. Do you understand that this number is bigger than p?
Yes.
Yeah, and there's your contradiction. So therefore, there are an infinite number of prime numbers. Isn't that pretty neat?
Yes.
That's a really neat proof. This was also done by Euclid. When did Euclid live? Song, impress me. 1500s?
When?
40.
Okay, this is ancient Greek.
BC something 40.
420.
I forget if it was like 400 BC or 400 AD. Somebody look it up.
Are we doing Euclidean algorithm?
Yeah. But that's easy. That's just an algorithm, yeah.
It's
Yeah,
definitely
it's fun.
420.
BC.
Yeah, 365 BC.
BC, like 400 to between 400 and 300 BC.
When he proved this.
Yeah.
Wow. The long.
Okay, there you go. So your homework is to, well, I did everything for you, right? No, you gotta understand these proofs because either 10 or 11 is gonna be on the test. Which one do you think it is? But now that you think that, I'm gonna put 10. But now that you think 10, I'm gonna put 11. Yoshida.
If you want to prove it for any other number than root 2, instead of using even, you would just say like divisible by 3.
Like root 3.
Like if you were doing root 3, then you would have to show that the same thing applies. Like if a squared is divisible by root 3, then a is divisible by root 3. Something like that.
Yeah, I don't
And then
know.
you
I don't
need
know
to-
about the root 3 one. That might require a different type of proof. I don't know.
It would be the same though, right? Because you would just use the same method except for instead of calling it
But then
even-
this would be 3 though. Yeah?
Instead of calling it even, you just say it's divisible by 3. Because even is just like another substitute for
Oh,
divisible by
yeah.
3.
Divisible by 3. And then you're also going to get the other one is divisible by 3. Therefore, it can't be in lowest terms, yeah? Okay, that makes sense? Okay, we're done.
Yeah.
Let's go to lunch. And then, when do I see you next? Do I see you? Yes, I do, on Monday. We finally did the last one, indirect proof. Now, here's the question. Do you guys want to take the test before vacation or after vacation? Are you going to remember all
Not
this?
after
No,
vacation.
Or probably not.
Let's do it before.
During.
Wait. What's that again, son? We probably going to forget.
No, we gotta remember.
The best math students in the school probably going to forget.
No.
No.
Wait. Do you forget how to play tennis?
No.
Okay then. What's the problem? Okay, so you guys want to take it next week, Wednesday then? Last period of the day?
Oh.
That sounds fun.
Wait.
No, this test is really easy. You're going to be able to finish this test in less than 30 minutes.
30.
Well, how many questions?
The hardest problem is going to be probably find the last 3 digits
Because
of
it's
something to the
complicated.
yeah.
That's 3 digits of root 2.
Is it easier than the,
Huh?
is it easier than the logic test?
No.
Last 3 digits of the largest prime number.
All right.
How's the, you can't-
Oh, God.
Really?
Now I have to
I
upload
heard it was
the
an
video.
awesome